So now we're going to start chapter 2. Chapter 2, moving more and more into the unconventional realm, namely chapter 2 about asymptotic computing. So let me start sharing the slides. Right. So asymptotic computing, which is maybe sometimes also known as infinitary computing, we'll motivate that with a recap from a selected part of my cross-promoted lecture CS422, Theory of Computation, by recalling the halting problem. Halting problem is a provably undecidable problem, a problem that no Turing machine can solve, that no wild program can solve. And we will discuss in the rest of this chapter whether other ways, other models of computation, physical models of computation, may be able to solve the halting problem and thus may be able to refute the physical Church-Turing hypothesis. Let me say it again. The halting problem probably cannot be solved by a Turing machine. But it is an important problem in software testing, software verification. So let's try to think outside of the box of different ways, other ways of solving the halting problem, not using a Turing machine, but using other models of computation and other physical devices of computation. And the first such class of physical and models of computation are so-called Zeno machines, named after the Zeno's paradox. And we will discuss these machines and relativistic, Einstein special and general relativistic ways of realizing possibly such machines. And we'll discuss the power of such machines, revising computation, and Schoenfield's lemma from the theory of computation. Then we will discuss mechanical, asymptotic or infinitary computation and optical, asymptotic or infinitary computation. And we will discuss analog versions, analog computer of these Zeno machines. But this is already a cliffhanger and promotion for the next chapter 3. Chapter 3 will be about analog computing. Chapter 2 is still about digital computing, but infinitary computing. So this is our plan. And to start, let me remind you, we already mentioned how Alan Turing devised the model of computation, a mathematical model of a digital computer before the first digital computer became operational by Konrad Zuse. So 1941, Konrad Zuse said first digital computer became operational. And 5 years before that, Alan Turing published his famous paper on computable numbers with an application to the Entscheidungsproblem, where he made these 4 important contributions. First, he defined this mathematical model of a digital computer. He showed what it is going to be capable of, very powerful. Then he showed what are the fundamental limitations, what it is it not capable of, and thus providing guidance to engineers to realize this kind of computers. And this was, he was kind of guided himself by contributions in logic by Kurt Gödel, for example, who had proven 5 years before that there exist statements in mathematics, actually in number theory, which are true, but provably cannot be proven to be true. Now that sounds paradoxical, and that's exactly how Gödel's proof proceeded. He created a paradox. So, first observation is that there are uncountably many subsets of natural numbers, and therefore, but there are only countably many algorithms or Turing machines. So most of these subsets of natural numbers cannot be decided by an algorithm or a Turing machine. But Turing's contribution was to make explicit such a problem, namely the halting problem. So let's talk a little bit about the halting problem. The halting problem is the following question. Given an algorithm, A, and then given an input X to that algorithm, suppose, a thought experiment, hypothetically, suppose we execute that algorithm A on input X. Will it terminate, or will it run into an infinite loop? Now, everybody who has ever written a program probably also has written a faulty problem, right? And one common fault of a program is that it doesn't terminate. It keeps on running and running and running. So it's an important question whether the program terminates or not. And that answer to that question depends on which input is presented to that program. If we run the same program again with a different input, then maybe on the different input it does terminate. At another input it does not terminate, right? That happens, so it's very important for this question to include the input to the program, because the answer will depend not only on the algorithm that is hypothetically executed, but also on the input. And now we want that question to be answered by another algorithm. So now we have two algorithms. The input algorithm, which may change, we have a different input algorithm and a different input X. And we want one algorithm to answer that question for all possible input algorithms A and all possible inputs X. And this is the halting problem. Now let's try to solve that problem. That means let's try to devise an algorithm, let's call it B, which answers that problem. And maybe the first thought that comes to mind is, why not simulate the algorithm A on input X? Step by step, take the first instruction of A, simulate it, then take the next instruction, simulate it. Maybe next comes a loop instruction, check the loop condition. If it's true, then proceed to the loop body, and then simulate the loop body, instruction by instruction, then back to the loop condition. Is it now still satisfied or not? And so we can simulate that. And this is called a simulator or an interpreter. And that's a candidate for our algorithm B to solve the halting problem. However, this is not a solution. This does not solve the halting problem, because if the algorithm A on input X does not terminate, then our interpreter or simulator will also keep simulating instruction by instruction of algorithm A without ever reaching the end instruction of algorithm A. Of course, algorithm A may not terminate, in which case our simulator or interpreter will never proceed to say, no, this algorithm terminates. If our simulator interpreter eventually arrives at the end instruction of the algorithm A, then it will say, yes, algorithm A on input X terminates. But if it never arrives there, then it will never produce an out answer. And in particular, it will never say no. So that's not a solution to the halting problem, because for a solution, we require algorithmic solution to always answer correctly. And our simulator will not always answer. It will also always give a correct answer, but sometimes it will give no answer at all. And what Turing proved is that there is no algorithm which can do that. Our interpreter is not an answer, so does not solve it, but there exists no algorithm B which always correctly answers this question. And this is the undecidability of the halting problem. Always correctly answer. And Turing's proof is actually pretty easy to understand and to follow to anyone. And that's why I repeat this here. Students of computer science really must know this proof because it's so simple. It requires no background, no studying, just a clear thought and a clear mind. And other students are highly recommended to know that and to understand that. Because it's a mathematical proof that everybody can understand, and it's a proof by contradiction. So there are some mathematical proofs that everybody should know, like, for example, the proof that there are infinitely many prime numbers. Everybody who graduates from KAIST should know that proof. And another one is here, undecidability of the halting problem. Proof by contradiction. We suppose that there exists such an algorithm B, and then we lead that to a contradiction. So here's a hypothetical algorithm B, which receives as input A, any algorithm A, and it receives at input X, any input to the algorithm A, and then it performs some calculation, and eventually, that's important, it will produce an answer, yes or no, plus or minus, but this answer is supposed to come always, as opposed to our interpreter, or a simulator, which sometimes doesn't produce an answer ever, and it must always be correct. So no heuristics allowed here. But then we use that hypothetical algorithm B and convert that to another hypothetical algorithm B prime. So converting hypothetical algorithm B to another hypothetical algorithm B prime uses B as a subroutine. B prime receives as input only one algorithm. And then it executes the hypothetical algorithm B prime as a subroutine call on input A and A. So here we had input A and X. Now we have input A and A. Is that a strange thing? Well, remember that our algorithms are always encoded and encodable as natural numbers. So when X is a natural number, we can assign particular value to that natural number, namely the code of the algorithm B. That's what happens in compilers, right? A compiler receives as input an algorithm and it produces something. A simulator receives as input an algorithm. So that's a common thing to have some input, which is an algorithm. And now our algorithm B prime makes a subroutine call to this B, and then it expects to return the answer of algorithm B. If the algorithm call to algorithm B returns plus, if it says yes, it terminates, then our algorithm B prime will deliberately enter an infinite loop. You can do that, right? Create an infinite loop that doesn't terminate is easy. Whereas if the subroutine call reports no, minus, then our algorithm B prime will use that answer and simply terminate. That's the arrow here, symbol of that. So if algorithm B exists, then also algorithm B prime exists. Now let's look at the behavior of this algorithm B prime when executed on input B prime, its own input. That's the famous paradox, the self-reference, the strange loop, as called by the Gödel-Escher-Bach book. And again, let me emphasize, it is nothing unusual to have an algorithm be presented with itself as input. As a matter of fact, that's how the GNU compilers work, right? So when you receive a Linux system, it comes with a very simple, basic compiler, and then maybe you download the GNU compiler source from the internet and compile the powerful GNU compiler on your powerless basic C compiler, system C compiler. And what then happens is, then the GNU compiler compiles itself a second time with all optimizations turned on to produce a highly optimized version of itself. So the GNU compiler installation process involves compiling itself, having itself as input process. And this is what we do here. Only here we do it as hypothetically as a thought experiment based on the hypothesis that algorithm B exists and therefore also algorithm B prime exists. Now let's see what algorithm B prime does when presented with input B prime. There are two possible scenarios. Either algorithm B prime on input B prime does terminate, or algorithm B prime on input B prime does not terminate. Let's consider both scenarios. There's no third choice, right? Tertium non datur, as logicians say. So let's first consider the case that algorithm B prime on input B prime does terminate. Does terminate means that the subroutine call reported minus, reported no. Reporting no means, by the hypothesis on algorithm B, no means that algorithm B prime on input B prime does not terminate. But we're just considering the case where algorithm B prime on input B prime does terminate. So that's a contradiction. Well, this cannot be the case. Therefore, let's move on to the other case, the case where algorithm B prime on input B prime does not terminate, enter this infinite loop. Now, when does that happen? That happens when the subroutine call reported plus, reported yes. Reporting plus by hypothesis means, since B prime is supposed to solve the halting problem, it means that algorithm B prime on input B prime does terminate. But we're just considering the case where it does not terminate. So again, a contradiction. So in both cases, we arrive at a contradiction, which means that, yeah, there is no third case. So the only conclusion, the only resolution to this paradox is that algorithm B prime cannot exist. There cannot exist an algorithm B prime, which on input B prime leads to these contradictions. But if algorithm B prime with this behavior does not exist, then also algorithm B cannot exist, which is the contradiction which proves that no algorithm B can solve the halting problem always and correctly answer that question. So this was a testimony of Turing's ingenuity that hopefully every one of you has been able to follow this proof. If it takes some time to digest, and I recommend you look at this again at home, look at the slides, look at the recording, and see how simple and transparent this proof is. You don't need to understand any any background, only just a little bit about making subroutine calls with different formal and actual parameters and some logical thinking. So now time is already running out. So I leave it at that. And so tomorrow we're going to resume and continue and discuss possibilities of approximating the halting problem using classical conventional computers. And then we move on to unconventional approaches to solving the halting problem using asymptotic computation and infinitary computation. So That's all for today. Thank you very much for your attention, and see you again tomorrow. Goodbye.